Okay, first, anyone have any homework questions? Last time I gave the definition of the centroid. I want to show just one example of how to use that integral formula. You're not going to have to do that. You're just going to have to use the shapes like the example I did of the center of mass of Minnesota last time. Okay, so let me do an example. This is the integral definition of the centroid. And so I gave you the formula for a right triangle. So if you have, and I give it facing the other way, but I'm going to draw it this way just to sort of emphasize that the direction doesn't matter. You have to think of these centroid values as distances from landmarks. So let's say we have this right triangle and the centroid is here. And let's call this distance h and this distance b, base. Then the distance from, so you can always think whatever axis you're looking along, whichever leg you're looking along, there's like a high side and a point side, and the centroid formula gives you the distance from the wall side going toward the point side. Okay, and so if you flip it around, you have to flip that measurement around too. So this distance here is b over 3. And this distance here is h over 3. So now we're going to derive that using the integral definition. All right, so let's say, well, I'm going to orient it this way. This is 90 degrees, and this is going to be B, the base, and this is going to be H. And I'm going to put the coordinate system, the origin, at the point. So this is the positive x-axis, and this is the positive y-axis. And the definition of the centroid, so x bar, y bar, is equal to 1 over the total area times the integral over the whole area of the coordinates of each individual infinitesimal mass times, or infinitesimal piece of area, I guess, times that infinitesimal area. Okay, so that's the definition. And we're going to break it up like this. And with an integral, using any kind of integral definition, really the trick to coming up with an answer is coming up with the right way to break up this thing into these infinitesimal pieces. like if we were doing this with a disk, we'd probably want to use some kind of polar coordinates or something. It would make more sense. Um, with this one, if you try to do it in polar coordinates, you'd be here all day. You'd probably still not come up with a good way to answer it. But so what we're going to do is our dAs are going to be these, like in the definition of a Riemann sum when you first talked about integrals. We're going to break it up into pieces like this. And let's start figuring out what some of these values are. So the area is base times height over 2. Okay, so 1 over the area is going to be 2 over base times height. And then for this little strip here, we have to figure out, so this is our dA, okay? This is one of our dAs. And so we have to figure out the area of that. That's going to be our dA. And we have to come up with the x and y. And actually, since this is not, since this doesn't have infinitesimal dimensions in every direction, what we have to do here is come up with the centroid of that. I mean, that's easy to do, right? But so we need the coordinates of the centroid of that piece. So this is what we need the coordinates of. That's really the center of mass symbol, but I don't have a centroid symbol. All right, so now if we think of doing this in terms of x, because we're going to have to choose some variable to integrate this over. Let's think of our independent variable as x. We have to represent all this stuff in terms of x. Okay, so we have to represent this infinitesimal area in terms of x, and we have to represent the coordinates of the centroid in terms of x. Well, the x location of this thing is just going to be x, right? Actually, let's do the dA first, and then I think it'll be easier to. So this dA for a given x value, for any x value, our dA is going to be just the height of that times the thickness of it. So that's going to be y times dx. Okay, are you with me on that? So for a given, we need to do this for every one of these strips. They all have different x values. But for any given x value, it's going to be the associated y, the height of this, times the thickness. That's just the area of a rectangle. Okay. Well, that y is not in terms of x, and we need it to be. So how are we going to come up with y in terms of x? Well, you can see that the y value that we're talking about, the height of this rectangle, is just the value along this linear function. So if we can come up with the function y equals mx plus b that represents this, then we can come up with that height in terms of the x value. We're not going to have to solve for it. We just want it as a function. But what we're going to do is so the y value is going to be equal to mx plus b. Okay. And we just want to represent this diagonal line, that hypotenuse. Okay, so how are we going to do that? B, what's the y-intercept? When x is equal to 0, y is equal to 0. So that's 0. And then the slope, well, we know that over this line. If you follow this line, by the time you've risen h, you've had a run of b. So that slope is h over b. And so for any x value, the associated y value is hx over b. Okay, so now we can rewrite our dA, for any x value, the area of that little infinitesimal strip, dA is hx over b dx. Okay. And h and b, you know, those are known. Those are just constants that represent our specific triangle. Okay, so we have that. Now what about so what else do we need? For this formula, we know the total area, so we got that. Now we have a representation for dA for any x value, we have that. Now all we need is a representation of the coordinates of the centroid of that strip for each x. Okay. Well, we have the x value, it's x. Okay. Now we just need the y value of that centroid. And given that we know the y value at the top of this rectangle, what's the y value at the middle of this rectangle? Half of that. Yep, it's just the midpoint. So the y centroid of the infinitesimal strip is, 1/2 of the y value at the top of the strip. And so that means that the x and y value for our strip for the centroid is going to be, well, x for x. But for y, it's going to be 1/2 of this, right? This formula that we got. This represents the, the point at the top of the infinitesimal strip. That's the point on the line. And so this is going to be, so if that formula is hx over b, this is going to be hx over 2b. No. So we're imagining that this thickness, so the thing that makes it infinitesimal is the thickness. So we're imagining this doesn't have any thickness. So on one side, it's like, so you go up x to get to this thing, and then to get to the left side, you'd have to go back 1/2 of a dx, which is nothing. And to the right side, it would be plus 1/2 a dx, which is nothing. So the whole thing we're just imagining being at the location x. Because this one, now for this one, we're not talking about the area, we're just talking about the location. Okay, so now let's put it all into that integral formula. So we have everything now put into the integral formula. And you get the centroid is equal to 1 over the area, that's 2 over BH, times the integral of the vector x hx over 2b times our dA, which is hx over b dx, and we need boundaries for this. What are our boundaries going to be? 0 to b, yep, because we're doing it in terms of x, so it's the boundaries of the x values. And so if we put this together, I'm going to multiply this one at the end. So 2, so I'm going to keep this on the outside, the 2 over BH. And the integral from 0 to b is going to be, for the x value, hx squared over b. And for the y value, it's going to be h squared x squared over 2b squared. Dx. And now integrate that. I'm going to still keep this outside. So we have the 2 over BH. And if we integrate that first one, we get hx cubed. We're integrating with respect to x. These other things are just constant. So hx cubed over 3b. And for the y component, we have h squared x cubed over 6b squared. And we're evaluating this from x equals 0 to x equals b. Plug in these values. If you plug in 0, you get nothing. So all we have to do is plug in b. So we get hx cubed. Nope, I didn't plug it in. hb cubed over 3b for the x component. And for the y component, we get h squared b cubed over 6b squared. You can cancel some of this stuff. So cancel one of those b's. And cancel 2 of these b's. And then plug in, then multiply by the 2 over bh, and you get 2h over 3. No, the 8, okay. What I wrote is right? You get you cancel the 2, I'm trying to talk while I think. The 2 h's cancel, one of the b's cancels, you get 2b over 3. And then for the second one, multiply that. You cancel, so the b's cancel, this b and this b cancel, one of the h's cancel, and you get 2h over 6, which is h over 3. Okay, so this is x bar, y bar. And so let's think about what we calculated, because that looks a little bit different than the formula that I gave you. So we calculated for a triangle going this way, the centroid is over here. And we calculated that this distance is h over 3. And we calculated that this distance is 2b over 3. But since the whole thing is b, that means that this distance is b over 3. Okay, and so the formula that's given, that I gave you last time, is that the height from the flat side of the centroid is h over 3, and the distance from the flat side to the centroid is b over 3.
You just proved the formula.
Yeah, that's right.
Will we be using this to find
No, I don't think there are any problems that I assigned where you have to use that integral formula. I just want you to see one of them. But you can see from this why using that centroid formula doesn't end up being that useful a thing usually, because any shape that anybody's ever done the centroid formula for, they've come up with a simple algebraic formula that you can use from then on, you know. So all you you never have to use the centroid formula if you have a smart friend, you know, or if you had a smart older brother or whatever. They already did it. And then also, because of the sum formula, I mentioned this before too. So say you wanted to calculate the centroid of this shape, okay? That's a mess, but if you break it up into skinny rectangles, and you can think of it as the sum of all these skinny rectangles, okay? And as long as you make them skinny enough, you can get it as precise as you want. And so you most likely do this with a computer program, not by hand. But you just figure out what the centroid was of each of these rectangles, which is easy because of the symmetry. And then you just add up, you know, use the sum formula to come up with the centroid of the whole complicated shape. Yep. It depends on the. So yes, if it was a uniform thickness the whole way, then yes, that would be the most sensible way to do it. If it's, I mean, if it had some other, sometimes you'd have to find different patterns than that. And so, sort of the same as when you're using an integral formula in 2D, the sort of the key to the whole thing is figuring out how to break it up into the infinitesimal three-dimensional pieces. You know, are you going to do it as a bunch of as a bunch of disks? You know, if it has an axis of symmetry, you know, you could do it as a bunch of disks. You remember sort of thinking this way in Calc 3, too? Yeah, okay. Yeah, solids of revolution or something. Okay. Any other questions about that? Okay, what if you have what if you need the centroid of a non-right triangle? Because that calculation I just did and the formula I gave you last time is just for right triangles. So what if you had to do a triangle like that, or a triangle like that? Well, the key idea is you can always break up any triangle into a combination of right triangles. So just make this into this and use the sum formula. Make this into this and use the sum formula. Okay, so that right triangle formula is really all you need. Well, it depends. If it's symmetric, you're right. But if it's asymmetric, then you have to do the calculation. But yeah, if it's isosceles, then you're thinking about it right. Yeah. Would you take the? No, you'd use this form. You'd use the sum formula. You'd use this xy is equal to 1 over a total times the sum of the centroid of the individual piece times the area of the individual piece. By the way, often, like this is an example where doing that would actually be sort of a hard way to do it. An easier way to do this, most likely with the dimensions that you'd be given for something like this, would be to think of the big triangle and subtract the little triangle. Use the sum formula in subtraction. Okay. So now going back to thinking overall about rigid body kinetics. The equations of motion are Newton's second law. So that says add up all the forces on the chosen body, and that's equal to the mass of the chosen body times the acceleration of its center of mass. Okay. Now we know what this is, we know what this is, we know what this is. So we're good on Newton's second law. And then the second one, equation of motion, second vector equation of motion, is the moment equation, rotational Newton's second law. And that says that if you add up all the moments around the about point, that's equal to the mass moment of inertia around the about point times the angular acceleration vector. And then there are some restrictions on what that A is. A is either, what are the possibilities? Yep. And does everybody have a fixed point? No. Only bodies that have a hinge that connect it to the ground or whatever your coordinate system is. And for things that don't have a fixed point, what's the other option? Center of mass, that's right. Okay, so we're okay with this. We're okay with the idea of a fixed point. We know what the angular acceleration is. So we just have two more definitions we need before we can do problems. We need to talk about the definition of the mass moment of inertia. And we need to talk about what a moment is. Okay? So we're going to start with the mass moment of inertia. um, about a point. This is the way to think about it. You'll see that usually people, when they're talking about this, just call it the moment of inertia. The variable that we're going to use for this is going to be a capital I sub A. So we'll get to that as we go through because you'll see from the definition what the units are. Okay, so there's one thing to be really careful about here. So people are going to just call it the moment of inertia, but that obscures an important difference with something that's going to come up in the next few weeks in D-form. So be careful. In D-form, there's the area moment of inertia about a point. Just like this one, people call it, so it's called just the moment of inertia. And it's given the variable name capital I sub A. Okay, so it's really easy to get these two mixed up. The area moment of inertia is a measure of, so it measures a cross section's resistance to bending the mass moment of inertia measures a rigid body's resistance to rotation. So this is the one that we're dealing with, talking about the ability to rotate a rigid body. And you can think of the mass moment of inertia as being exactly a rotationally analogous to mass in translation. Okay, like a mass is something that resists acceleration. The mass moment of inertia tells you how well a body will resist angular acceleration. Okay, so if you have a big mass moment of inertia, it takes a lot to get it rotating. If you have a small mass moment of inertia, it's easy to get it rotating. And that's without any consideration of what other loads are acting on it, whether it's on the ground, whether there's friction or anything like that. Out in outer space, if you ran into a semi truck, it would hurt. You know what I mean? Because it would be really hard to accelerate it down to rest. You know what I mean? And that doesn't have to do with its wheels being on the ground or whatever. That's just a property of its mass. And it's the same thing if in outer space, if you tried to get a semi, if you had a semi truck in outer space connected to a hinge, that would be so weird. But once you got like used to that idea and you tried to rotate it, it would be hard. And it doesn't have anything to do with friction or anything like that. It just has to do with the mass moment of inertia. Okay. So the integral definition of the mass moment of inertia. No, let me not give you that yet. Let me tell you what the idea is. So something with a big mass moment of inertia has a lot of mass situated far from the axis of rotation. Okay, so let me show you an example. In gymnastics or diving, any kind of acrobatic sport, there are different ways you can position your body to do flips, and so I'm going to think of sort of the two extreme versions of this. Okay, so here's one way, if someone does like a double backflip like this, they get a lot of points for that because it's really hard. Or someone could do a double backflip this way. Well, it's also very hard, but they get a lot less points for it because it's not nearly as hard as this. Okay. You get a lot more points for this because it's hard to get this rotating. And since it's hard to get this rotating, you have to get up a lot higher in the air in order to finish two flips with your body in this position. Someone who's really good at that tight position, they don't have to get up that high in the air to finish two flips like this. So relatively to the other one, this is easy to rotate. And the reason is, so do either of these have fixed points? No. So you have to think about this then as the axis of rotation being their centers of mass, which is like here and here. What? Well, that's pretty close to where it is, but the center of mass is, yeah, it's somewhere in your torso. But just the way these equations work mean that in order to think about this intuitively, you have to choose the center of mass as what it's rotating around, unless it has a specific hinge to the ground. It does, yeah. So let's think about what's going on a little bit. So say this is the same person, like their first time before they get tired, they do their double flip like this, and at the end they do it like that because they're tired. So this person has the same amount of mass, okay? So it's not harder to rotate this because the mass is higher. The difference is that here you can see if you broke this person up into little infinitesimal pieces of mass, a whole bunch of that mass is positioned at a big distance from the axis. Okay? And over here, the whole idea of this position is you're trying to get every part of your body as close to that axis of rotation as possible. Okay? So this has a big mass moment of inertia, and this has a small mass moment of inertia. Okay, so in this case, mass is situated far from the axis. And so that is a big mass moment of inertia. And in this case, mass is situated close to the axis. And so that's a small mass moment of inertia. You see the same thing in figure skating when people do the, so when people do their spins at the end of the, oh, you know why they do that spin at the end of the routine? Because they're super dizzy after they do it. So it'd actually be a lot more entertaining if they did it at the beginning. But okay, so someone starts their spin and they're all stretched out and they're going slow, and then the music swells and they pull their arms in and spin really fast. It's that same idea. The axis is down through their body. And so when their hands are out and their legs out like this and their heads back, they have more mass situated far from that axis of rotation. And it's hard to rotate that. And then when they pull everything in as tight as they can to that axis, they spin really fast. Yep. Well, we'll see that it's just from the axis. So you're talking about, so your center of mass is a point, and you're asking, like, does it matter whether they put their hands up? No, that doesn't matter. It's all, so there's just an axis like this, and it's how far you are from that axis. Yep. Yeah. Yep, exactly. Yep. Or like if you're on a carousel at a playground, and everybody sits in the middle, you can get it spinning really fast. If everybody's on the outside, it doesn't go as fast, although it feels a lot. If you're in the middle, you don't really feel the rotation that much, but it's easier to get it spinning fast. Okay, so now mass moment of inertia also has an integral definition. And just like with centroid, I'm going to give it to you. I'll do like one derivation, but mostly you're just going to use formulas for simple shapes. So the integral definition for the mass moment of inertia about a point. We're only doing this in 2D, so when I say a point, that'll be an axis in 3D. And that definition is I sub A is equal to the integral over the whole area of r squared dm where dm is an infinitesimal amount of mass and r is the distance from the point A. That's also, if it's in 3D, we're talking about an axis, but in 2D, that's a point to that piece of mass dm. Okay. Any questions about that? Okay, so on Friday, I'll do a quick derivation with this, and then I'll give you some formulas. And again, you know, we're going to have formulas for some simple shapes, and we'll be able to use those formulas for simple shapes and some kind of sum formula that I'll give you to build up complicated shapes from simple ones. And so we won't really ever need to use that integral definition. But it's nice to know what the definition is. Oh, let me write one more thing. This tells us what the units are. Yeah, so the SI units, well, what does that integral tell us? What are the units of dm? Kilograms. What are the units of r squared? Meters squared, so the SI units are meters squared kilograms. I guess people actually do it kilograms, meters squared usually. Okay, that's all.